To say that people hate the MiG-27 would be an understatement.
And if you ask me, the fact that the
Of
MiG-27
disintegration,
went
the
down in the
GSH
history of
630,
I've made my
nicknamed
thoughts on the
Gotcha by its
MiG-23
Indian
known
operators,
before.
has a reputation
One of the
for
worst
destroying
aircraft, if not the
planes
worst
with
aircraft of the
mountains,
Soviet
but it
Cold
doesn't do
War.
it by ripping itself
Fantastic.
clear of the
Despite their
air.
issues
Rather,
with the
that
MiG-23,
5,000 bucks
the
for
Microwave
the
Design
MiG
Bureau still went ahead with the MiG-27, a ground attack
Minecart
version
described it as the
flogger.
Even when the aircraft is praised, the most advanced variant is rarely mentioned or brushed aside by stating that it had a laser designator. Like, what are you talking about, Wikipedia? All variants after the MiG-27K had this feature. Why are you saying this?
Если что-то не успели мы другие дни недели, то не стоит огорчаться, на судьбу свою пенять. Если что-то не случилось или вдруг не получилось, значит можно все сначала с понедельника начать.
By the late 1960s, the USSR primarily relied on aircraft, such as the MiG-15 bis, MiG-17, and Su-7B, to carry out ground attack operations. The supersonic element of this force, that being the Su-7B, as time went on, became increasingly antiquated. Pilots complained about the need to visually identify targets out to 5 kilometers before they could be engaged. This was especially problematic at night or in poor weather conditions. These aircraft also lacked precision weaponry and were limited to dumb bombs, rockets, and cannons to destroy targets. The effectiveness of these bombs was low when they were deployed by Su-7B, as it lacked the ability to easily measure the distance of the aircraft to the target, determine the target's speed, and observe the target while its bombs were released. Of course, even with these deficiencies, pilots did exist who could make expert use of the aircraft, and in many units a slogan was adopted by those who scored excellent marks during training endeavors. Every bomb, every round, on target. The issue was that many of these so-called experts had done much of their training on the same range against the same targets with the same munitions hundreds of times. When it came time for them to partake in large-scale exercises that sought to simulate real combat conditions, their confidence was usually crushed. An aircraft that could get into the air faster, land easier, and operate more advanced avionics was needed. Chief designer N.G. Zirin, who was working on improving the Su-7B, was discouraged by management from Komsomolsk-on-Amur, who were already tied up producing the older model. It was for this reason that Mikoyan was able to propose several concepts that would be able to fill this gap, notably the 23SH-27 and 2711. In 1970, 2311-4 was equipped with the ASP-PF PBK-2 sighting system, but ultimately fell short of the MiG-23SH, which aroused great interest due to its application of an existing airframe. Work on the project was quickly approved in August of that year, and by November, requirements had already been drafted. This new fighter-bomber was to be capable of engaging large and small targets alike with relative precision, without breaking line of sight. MMZ Zenit, the team tasked with realizing the MiG-23B as it was designated, was under immense pressure to deliver a product as quickly as possible. Deadlines were unusually short, and so preparation to produce the aircraft was carried out alongside its development. Zenit was led by G.A. Siedov, MiG-23B's chief designer, and his deputy, G.P. Dementiev, who was tasked with intermediating between the Ministry of Defense and the team. The MiG-23B would differ from its air superiority fighter counterpart through the introduction of an entirely new nose and cockpit layout. In place of the radar was the new Sokol 23S sighting and navigation complex developed by the Leningrad Design Bureau Elektro-Avtomatika. Sokol 23S included the PBK 3-23S bomb sight, which was assisted by an analog computing device. the S-17VG optical sight, the FON laser rangefinder, and the KN-23 navigation system. The automatic control system, SAU-23A, was replaced with the new SAU-23B. The front of the aircraft was optimized to provide superb visibility of ground targets, which was thoroughly enjoyed by its operators, and would later glean the aircraft the nickname the Flying Balcony. The last addition present on this early proposal was 3 hardpoints added to the fuselage, which meant the MiG-23B was capable of carrying an additional 3 tons of bombs. It was also planned to introduce armor plating on the sides of the cockpit to increase the survivability of the aircraft against ground fire. The AL-21F3 engine was chosen for the MiG-23B as it was considered more economical at subsonic and transonic speeds. The first prototype, designated MiG-23B 3224-1, was manufactured in January 1971. On February 18th, after the system was inspected, A.V. Fedotov conducted a successful test flight. That same year, 2 more prototypes, 3224-2 and 3224-3 were built, with 3224-3 serving as a pre-production example. The MiG-23B's maximum flight speed was 1,880 km per hour, which dropped to 1,350 km per hour at low altitude. Further tests determined that its performance was indeed acceptable, and in 1972, serial production began at MMZ Znamie Truda. This was a short-lived endeavor, as in October of 1973 a decision was made to unify the power plants of the MiG-23 family. As a result, the MiG-23B was fitted with the R-296-300 engine, a slightly modified version of the R-29-300 used on the MiG-23M. This engine was first tested on MiG-23B number 3016. The introduction of this engine prompted a new designation, MiG-23BN, which replaced the MiG-23B later that year, with number 3321 being the first. This model would become more common on the export market. From 1972 to 1985, 49 MiG-23Bs and 575 MiG-23BNs were produced according to Mikoyan. The MiG-23BM would soon be introduced, which was conceptualized in December of 1971 to improve upon the MiG-23B's expected shortcomings. Since the aircraft was not intended for high-speed supersonic flight, the variable intake ramps present on earlier models were removed. The cockpit finally got its reinforcements, as this had not been implemented on MiG-23B, and the more advanced PRNK-23 sighting navigation complex was installed, which integrated the BCVM or Beta 10-15-23 computer. Compared to the Sokol 23S, the introduction of a digital computer significantly improved the accuracy at which the aircraft could engage targets. The MiG-23BM was also fitted with the SAU-23B-1. Changes were also introduced to increase the ease of takeoff and landing. As on earlier models, if the control stick was pulled too far during takeoff, the fuselage keel could catch on the concrete, causing deformations. New tires with greater width than their predecessors were fitted to compensate for the increased weight of the aircraft during takeoff and landing. The size increase required cutouts to be made on the landing gear doors so that they could retract without issue. Arguably, the most important and recognizable introduction on the MiG-23BM was the removal of the 23mm Gachet 23L cannon in favor of the exceedingly controversial lightened version of the 30mm AO-18, designated Gachet 6-30. This weapon carried 260 rounds of ammunition, and had a rate of fire of 6,000 rounds per minute. It is difficult to say if this cannon was specifically designed for ripping open tanks, as it was more suited towards destroying aircraft on runways, hitting command posts, and other various targets that were commonly engaged by the cannon in training endeavors. Mounting this cannon to the aircraft was a difficult task, as it had a recoil impulse of 5.5 metric tons of force. The shock waves produced with each round had negative effects upon the fuselage due to the barrel's proximity. While this has been the subject of great mockery, Mikoyan themselves stated that the solution was rather straightforward. First, the airframe was reinforced where the vibrations were most intense. Next, the cannon assembly was canted by 11 to 13 degrees, bringing it a safe distance from the airframe. Lastly, the fire control system was adjusted to compensate for this solution. To protect the airframe from high-temperature powder gases, the gun compartment was sealed, and the walls were lined with heat-resistant material. An additional armored partition was installed between the gun and the fuel tanks. While it is true that incidents occurred where the aircraft was damaged by this gun, it was only during initial tests before the weapon had been streamlined. Many of the issues associated with the weapon were derived from its first production batch, which was exceedingly problematic. These early guns required a 15-minute cooling period after 150 rounds had been expended. The Ijevsk machine-building plant worked to eliminate many of these problems and eventually refined the gun to a point where it could deliver 300 rounds in a single burst. Despite its reputation, the MiG-27 was actually evaluated as one of the safest aircraft in service. This is supported by its accident rate of only 25 MiG-27s lost. 2/3, or 18 aircraft, were due to pilot error. I would like to reiterate a few points relating to the gun debacle. The famous tales of MiG-27's instrument panel falling off, landing gear jamming, and various subsystems breaking from the simple act of firing the cannon are nonsensical. My annoyance towards this subject comes from a severe lack of analysis by those who peddle these myths. I want to begin this semi-scripted rant by making it very clear that MiG-27's gun was not intended for shooting at armored targets. The ammunition employed by Gauchat 6-30 is described as follows. The explosive block inserted into the body cavity provides fragmentation, blast, and incendiary effects of the projectile. A lead ring pressed into the threaded groove of the fuse during assembly is installed to protect the projectile cavity from blow-by propellant gases. Upon the projectile meeting an obstacle as a result of the fuse actuation, with a delay, the projectile ruptures. This is not an armor-piercing round. This round was not designed to defeat tanks. The reason this cannon was included was to provide the ability to engage exceedingly short bursts on targets with moderate accuracy. For this reason, the cannon is much more accurately viewed as an S-5 rocket pod always available to the plane, no matter its configuration. This is why it was retained on MiG-27K. If it did not serve a purpose, it would not have been included on this model. The weight reduction programs would have most certainly claimed it. Second, I have to say, no, firing the cannon under normal conditions will not destroy the aircraft. These guns were fired with extreme consistency. It would be hyperbole with a degree of accuracy to say that they shot them every day across the USSR. They were used during every training endeavor, and every pilot had to qualify on it. And with such a small number of mechanical errors contributing to accidents, it was unlikely that issues were arising after the revisions conducted in the late 70s that reduced its rate of fire to 4,000 RPM and added more reinforcements. Here, application of the gun was momentarily restricted, but this was lifted after these changes. The instrument panel story is especially telling because it could not have been caused by the gun. I'm not going to go into detail on how MiG-27's instrument panel is attached, but I have to say that the means in which this is engaged make it physically impossible under normal circumstances for the gun to shake it from its position within the cockpit. These instrument panels are designed to withstand far greater forces than the vibration of the cannon, and in this case, it was most likely a poorly secured instrument panel, as this is truly the only situation it could have been freed from its constraints. It is especially interesting to me that most of these cannon-related incidents occurred in the late 80s, when maintenance crew performance was at an all-time low. This was exacerbated by the fact that Gauchat 630 was a very complex gun requiring preparation and cleaning after every use. Supposedly, these incidents grew exponentially in the late 80s and early 90s before the collapse. I wonder why. Issues like poorly secured fuses being shaken out of place or unburned powder remaining in the barrel igniting rounds, causing premature detonations, damaging the aircraft, are very telling that this was not a cannon problem. It was a maintenance problem. The only other case I can find where premature detonations occurred in the barrel due to unfamiliar ground crews would be in 1978, and that's understandable considering the aircraft had literally just entered service. The issue with landing lights is also frequently misconstrued, even by people who should know what they're talking about. It wasn't that they were destroyed by the recoil. That is insane. It was caused by fragmentation off the ground grazing the aircraft, which had an easy time startling careless pilots. They weren't removed before training endeavors. The manual says they were to be inspected after and before flight to ensure that they were not damaged by fragmentation and had a risk of breaking. Despite all of the strange happenings described vaguely related to the gun, I believe that the reality of the situation lies with Gisha 630 being especially good at exposing manufacturing or maintenance failures, which only accounted for a small number of write-offs. The link ejector was also notoriously unreliable at the outset of service and at the end of its service, which can be blamed for a lot of these problems as well. Previously produced aircraft still using the problematic cannon were modified according to Bulletin number 2325-137DK. On the 17th of November 1972, V.E. Minitsky conducted a successful test flight of the first MiG-23BM prototype, 3225-1. This machine, along with the second prototype and the first 5 serial MiG-23BMs produced in 1973, still used the AL-21F-3 engine. But from 1974 onward, serial production was carried out with the R-29B-300 being standard. State trials were completed in December of 1974, and in February of the following year the MiG-23BM was accepted into service under the designation MiG-27. The aircraft was produced at the Irkutsk machine building plant. 360 were manufactured between 1973 and 1977. In February of 1972, before the MiG-27 had been finalized, a concept was proposed and its development pursued in the background. This would lead to the MiG-23BK. It would differ from the MiG-23BM through the introduction of the Orbita 20-23K digital computer and the Kyra targeting system, unified in the PRNK-23K sighting navigation complex, all of which would allow this aircraft, eventually designated MiG-27K, to become the most advanced Soviet fighter bomber of its era.
Что поделать, я, конечно, рассуждаю по-земному, и за это ты, медведица, меня прости. Но сияла и смотрелась ты совсем бы по-другому, если б твой большой медведь сиял поблизости. Чья здесь вина, может, пойму, ты мне ответь. Вечно одна, ты почему? Где твой медведь? Чья здесь вина, может, пойму, ты мне ответь. Вечно одна, ты почему? Где твой медведь? Где твой медведь?
The MiG-23BK was born from the inefficacy of the KH-23, which had an unsatisfactory launch range and required visual guidance. For this reason, the weapon was primarily limited to hitting large, static targets after air defense had been suppressed. After launching the missile, as to not break its guidance, the pilot could not maneuver and had to direct all of his attention towards keeping the missile in front of him. If the aircraft came under fire from anti-aircraft weapons, the pilot would not be able to guide the missile and would have to maneuver to save his own life. This left a lasting impression on frontline aviation, who began to believe that precision weapons were too much hassle and that unguided rocket barrages were far more convenient. Initially, the application of radar sights was proposed, as they allowed for the detection of targets and landmarks in any weather, day or night, but these were far too heavy and therefore a less conventional solution was needed. The requirements for this new targeting complex were difficult to say the least. The developers had to solve two problems at once: improve the aircraft's detection capabilities and provide an accurate, somewhat autonomous targeting system to guide smart munitions. These issues were rectified by employing a television channel to designate targets and a laser rangefinder to engage them. The Moscow Design Bureau Geophysica, in collaboration with the Leningrad NPO Elektro-Optomatika and the Central Scientific Research Television Institute, got to work developing a new television sighting system. Specialists such as M.M. Sharapov, V.I. Karpenko, and A.A. Kazamarov were involved in its creation. This device would be known as Kyra, and was designed to detect targets on the ground, measure their slant range, and designate them for laser-guided munitions. The acronym used to describe the sight is LTXS, which stands for Laser Television Sighting System. I will be using this term from now on. The LTXS could be used when employing guided weapons with television and thermal seekers. Additionally, it could correct the aircraft's navigation system using visually observable landmarks. The device was designated Kyra 23 to differentiate it from the Kyra 24 to be employed on Su-24, and would integrate the 11S1 target illumination station and 16S1BS communications unit. Interestingly, there were also proposals to install Kyra on Su-17M4, alongside an even stranger proposal to incorporate the Geschoss 6-30 cannon. I don't know what they were smoking when they thought up. But back to the MiG-27. 16S1BS served to ensure the missile was in Kyra's line of sight and consisted of two modules placed behind the cockpit. Searching for and recognizing targets was carried out by the 11S1 through the KT-11S television channel, which included a TV camera designated KT-6.037, which employed a Vidicon tube. For the uninitiated, this served to convert the optical image into an electrical signal using a photosensitive semiconductor surface. After amplification and processing, the image was displayed on the monochrome IT-23 screen, which had 6 brightness settings. A funny anecdote from the IT-23 service manual is a precautionary statement that homemade fuses are forbidden and should not be used to repair the device. This is likely due to the system making use of fuses similar to the 576i, a standard in the civilian market. The name Kyra is likely derived from the difficult requirement of guiding munitions which lagged behind the aircraft after release. This was solved by allowing the sighting unit to maneuver from 0 to 160 degrees vertically and positive 35 degrees horizontally. This led to the team drawing parallels between the complex and the guillemot, a seabird commonly referenced as Kyra that could observe 2 different directions simultaneously while in flight. The first prototype MiG-23BK was prepared in 1974. This was difficult as the entire nose had to be reworked to accommodate the new equipment. 2 large windows were installed. The lower window housed 11S1, and the upper window the laser rangefinder's receiver, known as 9P, which fed information about the target's slant range to the aircraft's computer. Movement of the 9P's lens was synchronized with the TV sight and 11S1. Many supplementary systems had to be moved around to make way for the new electronics, like the SPS-141M jammer, which was placed at the front of the aircraft above Cairo 23. This jammer significantly increased the MiG-23BK's survivability against air defense weapons, and when compared to the older SPS-141 was far more efficient, as it introduced an additional jamming complex. The first complex is employed primarily against search radars to deny range and azimuth. It can operate continuously, intermittently, or mix the two. For azimuth deception, the station processes the received radar signal, modulates it in Block 112, then re-radiates it via the transmitting antennas, misleading the radar tracking channel. For range deception, false echoes are created by delaying pulses, thus creating echoes that appear at greater or lesser range than the real aircraft. The second complex is employed against radars actively tracking the aircraft. This is achieved through velocity data and azimuth deception, which is useful as it can be used against Doppler radars. The third complex provides mutual protection between two or more aircraft in a formation to mask the entire unit and make it especially difficult for singular radars to target any one aircraft. The manuals available to me which describe SPS-141M in detail are rather vague when it comes to the functionality of this third complex, and sadly the process of synchronization is not described. The fourth complex is automatically employed when being tracked while other complexes are in use. The complex is usually activated at low altitude and serves to project a false target with the same Doppler shift as the aircraft 30 degrees below the axis of flight, through both the forward and rear antenna, creating two false signatures. These signatures are of higher strength than that of the actual aircraft, and are in front of the aircraft as well as on the ground, positioned in such a way that velocity-gated missiles are likely to be diving onto the aircraft on a trajectory that allows the false target to overlap with the aircraft, driving the missile into the ground. This complex is specifically designed to diminish the efficacy of Hawk. Survivability of air defense was further increased with the introduction of SPO-15L in place of SPO-10, which could provide information on the type of radar tracking the aircraft, determine its bearing, mode of operation, alongside other characteristics. To accommodate the system, two wide-beam antennas were mounted beneath the air intakes to receive signals from the forward hemisphere. But this did not satisfy the design team. This solution was described as giving the aircraft elephant ears due to its perceived unsightly nature. Eventually, it was decided to mount them on the vertical stabilizer. Wind tunnel tests confirmed this did not diminish aerodynamic performance. SPO-15L is important as many features exist on this model that are exclusive to strike aircraft. SPO-15L can evaluate changes in signal parameters to identify the most dangerous radar when the aircraft is illuminated by multiple sources. These are broken down into primary and secondary threats depending on factors such as radar operating mode, aircraft altitude, maneuvering conditions, and the frequency or amplitude characteristics of the received signals. The system also tracks the approach of the main radar source by monitoring variations in signal parameters over time. The system displays these categories to the user through a color key, with green being radars observing the aircraft, yellow indicating a radar tracking the aircraft, and red signifying a missile pursuing the aircraft. It is likely that SPS-141M is automatically activated by SPO-15L, which chooses the target of jamming automatically by concluding which radar is of greatest threat to the aircraft. The new CVM-20-23K or Beta-20-23K digital computer installed within the prototype was a quantum leap capability-wise when compared to the older model mounted in MiG-27. It could handle 200,000 additions, 100,000 multiplications, and 10,000 divisions, making it 60% faster than our Beta-10-15-23. It also had greater memory than its predecessor, but as of writing it is unknown by how much this was increased. CVM-20-23K additionally controlled the entire PRNK complex. This computer also increased the speed in which pre-flight preparation could be conducted, as it was prepared via an onboard control console, with all of its necessary calibrations being recorded onto punch cards. PRNK-23K had 3 operating modes. The first was PMS, or Sighting by Aircraft Maneuver. This was used when firing unguided munitions, such as S-5 rockets, 30mm bursts from the cannon, or dumb bombs. This placed the sight in a fixed position relative to the aircraft. The next mode was PKS, or program-corrected tracking, which was used when launching guided missiles or dropping bombs from an offset point. The latter is done when the target is obscured by environmental conditions or terrain features. This problem is solved by using a reference point near or behind the target, which allows the computer to determine the actual target's position relative to the reference. AK, or autonomous correction, was used when launching guided missiles in the event of a computer failure. Here, the LTXS would keep the laser on the target using frame tracking. This was achieved by the system memorizing a frame where the target is clearly visible. When the image shifts from this frame, each subsequent frame is compared to the first, using the displacement of its contour points. This is used to generate signals sent to the gyro stabilizer, allowing the system to track the target by attempting to align the frames best as possible. This was a rather efficient methodology, as it allowed guidance to continue even if the target was barely visible, due to the fact it wasn't tracking the target itself but the entire image. AKS, or automatic corrected tracking, was the ideal mode of operation and was used in conditions where the target was clearly visible. AKS and AK employ similar principles, but in the case of AKS, the LTXS remained connected to the computer, which could provide more reliable tracking. Like in PKS or AK mode, the pilot still retained the ability to manually correct the munitions guidance if this was required, but unlike the previously described modes, AKS permitted rather aggressive maneuvers to be engaged by the pilot without breaking control of the weapon. 90-degree rolls with a rate of 30 degrees per second could be conducted alongside turns not exceeding overloads of 3 Gs. This significantly increased survivability of the aircraft when guiding munitions under fire. MiG-23BK featured the rather advanced IPP-2-53 head-up display. The development of this system warrants a video of its own, but I will only describe its relation to Kyra in this video. IPP-2-53 went through a grueling development cycle in an exceedingly short period of time to meet the schedule set for MiG-23BK. To accomplish this task, NIL-15 was reorganized. The head of the association, P.A. Yefimov, worked to recruit highly qualified electronic and optical specialists to realize the project in the wake of this reorganization. NIL-15 had to work alongside many organizations to create this system, notably the Moscow Electrolamp plant who handled the projection CRT, known as Kunitsa, and the Zagorsk optical mechanical plant who produced the Calameter. First, these organizations had to construct a mock-up of the IPP-2 to verify that there were no existing issues with the device. This had to be done before it could be mounted in an aircraft. Surprisingly, this mock-up proved highly successful and managed to meet all of the program's requirements. The application of a direct-view vector display allowed the projected symbols to be visible even in conditions of 100,000 lux. This mock-up gave way to the production of a prototype IPP-2-53, also known as Zrachok-2, for application within the MiG-23BK. IPP-2-53 consists of an indication unit, symbol generator, computation and conversion unit, low-voltage power supply unit, a frame for unifying all of these subsystems, and a frame for the indication unit to be mounted on the instrument panel. The computation and conversion unit exists to streamline the information provided by the navigation targeting complex. These analog signals are converted into digital signals and introduced via a common bus into the symbol generator. The frame housing the indication unit can be aligned using cold bore sighting, thanks to a ball bearing and 2 micrometer screws, with the aircraft jacked up beforehand. The Kunitsa CRT features circuits for distortion correction, burn protection, and automatic brightness control. The CRT has a diameter of 55mm and a length of 210mm. Initially, during the first phase of designing the Calameter, the application of a single-element lens was proposed. This was rejected because it did not fit the horizontal layout required for the indicator block. While evaluating alternatives, it was suggested to use a modified version of the well-known Petzval lens, which had a dual-lens configuration separated by a large air gap. This allowed for the optical axis to be bent 90 degrees, which aligned with the program requirements. In Zrachok-2, all lenses in the optical system are spherical. A version using some aspherical lenses was considered, which could have reduced the total number of lenses and the size of the rear elements. However, this design could not be implemented due to the plant's inability to manufacture aspherical lenses in sufficient quantities. Zrachok 2 is rather unique in that it has a relatively small instantaneous field of view of 9 by 12 degrees, compared to the total field of view of 25 degrees. This is caused by the small size of the exit lens, which is only around 100 millimeters. This limited the width of the indication block. To counteract this issue, the head can shift horizontally to aim at a target outside its instantaneous field of view. Vertical movement was more difficult. Eventually, it was determined that the simplest solution was to allow the mirror through which the pilot observes the HUD's symbology to automatically slide along guides to match the vertical position of the aiming mark. To prevent the mirror from bouncing back when the cannon fires, a worm gear and stops at the ends of the guides are included to lock it in place. In case the HUD fails or is rendered inoperable, a backup reticle is provided which operates via a stencil with an illuminator and a mechanism for inserting it into the focal plane of the optical system. This mechanism needed to be as accurate as possible, as cold bore sighting was performed using the reticle. The symbol generator uses permanent burn-in memory to store graphic elements. Circles and curved segments are approximated with short, straight lines. For example, a circle would be represented as an octagon. Before this method was approved, psychological evaluations were conducted which demonstrated that this was acceptable. Numbers, letters, and scale divisions have angular dimensions of 0.5 to 0.67. The GS and memory system are organized so that a single command from the navigation targeting control panel can display only the symbols required by a specific flight or combat mode, without cluttering the field of view with unnecessary information. IPP-2-53 is capable of displaying flight speed and altitude, vertical speed, acceleration, heading, bank, pitch of the aircraft, reticle, bomb fall line, trajectory, control index, deviation index, as well as warning signals and reference data. Serial production of the IPP-2-53 was carried out at the Jibaksuri instrument making plant. Interestingly, after evaluations of the reliability of each component on board MiG-23BK, IPP-2-53 was determined to be the most redundant subsystem. Another complication was that MiG-23BK had to have much of its instruments reorganized. The prototype was to include the Coral-1 short-range radio navigation system, R-832M and R-645 radio stations, APK-19M radio compass, RV-15 radio altimeter, and the SRO-2M transponder, which was later replaced in serial production with the SRO-1P. The side-slip angle sensor DUS-3M present on the prototype met a similar fate and was removed as it was not reliable, and was replaced by the DIS-7, which was far more accurate. Most of the cockpit instruments were reworked to accommodate these new systems. SAU-23BI and the SUV-2-26 weapon control systems were also included. To increase safety at high angles of attack, MiG-23BK was fitted with an angle of attack limiting system. The control stick was equipped with a travel limiter with a pusher that prevented bringing the aircraft to dangerous angles and stalling. Pulling the stick towards oneself caused the pusher rod to move forward, with its speed determined by the tempo of the nose-up movement, preventing any sudden dynamic overshoot to a larger angle. This mechanism was present in MiG-23s as well, and it was exactly this complex that allowed a MiG-23 to fly all the way to Belgium and then slam into a guy's house, which was a very tragic situation. One significant concern regarding the aircraft was the weight and size of Kyra-23. For example, 11S1 alone weighed 143 kilograms. This led to MiG-23BK having an unusually high forward center of gravity. To resolve this issue, the armor plates present on the cockpit were removed. This was an understandable reduction, as it was unlikely that these would prove useful in normal operating conditions. To further reduce the system's weight, the S-13 photographic control device was removed, which finally freed 1 ton from the aircraft. Despite these changes, MiG-27K remained an unusually heavy aircraft with a standard takeoff weight of around 17,650 kilograms. This led to certain pilots developing a fear of taxiing the aircraft, especially when turning was involved. MiG-23BK 3226-1 performed its first flight on December 30th of 1974. On the 18th of December that following year, a second prototype took to the air. Issues arose when attempting to install Kyra on an AN-26 alongside all manner of according equipment to perform rigorous testing of its capabilities and tolerances. This flying laboratory was called AN-26K. Due to minor issues experienced with Kyra dragging on until 1976, it was decided that it would actually be easier to just test the complex on the aircraft it was designed to be installed within. This turned out to be a functional solution. To quote lead engineer Sharapov, "Suddenly, many things started working out for us." This led to AN-26K taking an auxiliary role. In 1977, 2 additional MiG-23BK prototypes were produced. This led to NPO Geophysica being instructed to carry out the production of a test batch of 40 Kyra 23s. It was here that the powers that be decided things had been going far too well for the project's development staff, leading to issues beginning to present themselves in rather spectacular fashion. First, program-corrected tracking experienced significant difficulties. Orbita 20-23K was not fast enough to track target displacement while the aircraft was maneuvering. Similar problems had been encountered on Kyra 24, which was to be mounted on Su-24M, which required 4 years and over 1,000 test flights to resolve. The MiG-23BK, unlike the Su-24M, did not have the luxury of an additional pilot to manage the targeting system, which meant Kyra 23's complications could have taken even longer to solve. This led to additional automation being introduced as the algorithms required to engage certain targeting modes were streamlined. This was achieved in an exceedingly short period with considerable benefits. The MiG-23BK had never been more capable. After this revision, it was determined that a task requiring 7 MiG-27s would be accomplished by just 4 MiG-23BKs, with an additional 45% increase in survivability against air defense weapons. All of these improvements did not mean the team was out of the woods just yet, as Kyra remained temperamental. Manufacturing these complexes at scale was no easy task. The Irkutsk plant had to work overtime to produce even a small number of Kyra 23s, and often found themselves discouraged when subcomponents that had passed all relevant quality control inspections were sent back after they were examined prior to installation within the aircraft. Airframes without their targeting equipment began to pile up, and those that were being finalized were rejected with startling frequency. The plant director, V.A. Maximovsky, knew that if they failed, his workers would be left without bonuses, but at that time motivation was in short supply. He decided, in a desperate bid to inspire his subordinates, to go out of his way to purchase multiple luxury cars, which he promised to the most diligent workers once they had met their quota. This ended up being a highly successful strategy, and on July 26, 1980, the aircraft was accepted into service under the designation MiG-27K by the resolution of the Council of Ministers number 642-214. In total, by January of 1983, 215 MiG-27Ks had been built. During production, small modifications would be made to the aircraft, such as more ergonomic access hatches to serve as the targeting equipment. The 16th Tactical Air Army of the Group of Soviet Forces in Germany received their first MiG-27K in 1980. It was integrated within the 19th Guards Fighter Bomber Regiment, 1st Air Squadron. Interestingly, the MiG-27K was not used extensively or at all in Afghanistan when compared to its less advanced counterparts. Despite these aircraft being present in the 134th Fighter Bomber Aviation Regiment and the understanding that they possessed unrivaled capabilities compared to the rest of the formation, the terrain rendered them completely ineffective. In many cases, no matter the aircraft, targets could not be picked out from altitude without cues from a forward controller. Even Kyra failed to keep up with the short periods of engagement and small targets they were expected to destroy. This was partially a result of the recommendations to launch precision weapons at speeds of 800 to 1,000 km per hour from a shallow dive, at which point it was practically impossible to pick out a target and ensure the munition connected before they were gone. Another reason the MiG-27K was not used in Afghanistan was its lack of armor plating around the cockpit. Interestingly, evaluations conducted in the late 80s saw this revised. Modifications began in 1988 to improve the protection of these aircraft in 2 phases. Initially, limited up-armoring was permitted, but this eventually gave way to late production MiG-27Ks receiving large protective plates even bigger than what was originally intended for other MiG-27s, which was a very weird decision. I don't know why they decided to do this. It just made the aircraft way heavier than it should have been. In 1993, after the collapse of the USSR, it was decided that to reduce spending and streamline the Russian Federation's Air Force, older single-engine aircraft would be removed from service. This resulted in MiG-27s being transferred from storage to be decommissioned. A strike was held at the Irkutsk factory, as they did not want to scrap aircraft that they had constructed, especially the MiG-27K, which they had poured blood, sweat, and tears into producing. Mikoyan also protested to this decision, as there was no reason to liquidate perfectly functional MiG-27Ks that could still prove useful. These statements were vindicated by the First Chechen War, where strike aviation delivering precision weapons proved especially important. The prospect of reviving MiG-27Ks yet to be destroyed was considered, but it proved too expensive to reactivate them, and so the program never went anywhere. Due to the problems I mentioned at the beginning of this video regarding the effectiveness of KH-23, a new missile was needed to close the precision weapons gap. As the solution to this issue was being considered, NPO Geophysica made multiple breakthroughs in laser technology, which led to concepts immediately being proposed to exploit these innovations to solve the aforementioned issue. The Military-Industrial Commission wasted no time instructing the organization to produce a practical laser guidance system on the 26th of December 1968. The Leningrad State Optical Institute was tasked to assist Geophysica by developing the laser itself. Preliminary designs were prepared, and by 1971 requirements had been drafted for the KH-25. The most important of which was an accuracy of 6 to 8 meters. Alongside this missile, the Tushina Design Engineering Production Complex was tasked with developing a similar, heavier missile, designated US-KG, which would eventually become the KH-29. Those working on the KH-23 did not approve of this new missile, as it was being developed just as their project was finalized. It was only after the ability to fire multiple missiles at a single target was brought up that they were persuaded. KH-25 was intentionally kept nearly identical with the prior KH-23. Most major systems stayed the same, with the primary exception being that in KH-25, KH-23's radio control equipment in the tail was replaced with an additional F-25-2M warhead, which had an explosive mass of 13 kilograms, around the same as the mass of KH-23's radio control equipment. F-25-2M's asymmetric shape produced a nearly horizontal fragmentation spread, and its rear placement caused detonation at a greater height, enlarging the fragmentation area. This warhead was only added to offset the weight of the 24N1 laser seeker, which gave the KH-25 an unusual center of gravity. The primary F-25-1M warhead had an explosive mass of 80 kilograms. This was aided by asymmetrically arranged steel fragmentation elements in the forward section, which produced a more favorable fragmentation pattern than earlier designs. KH-25 had a maximum speed of 700 meters per second and a standard flight time of 25 seconds. Missile launch was often conducted at altitudes of 500 to 4,000 meters with a maximum range of 7 kilometers. The seeker was the missile's most novel and technically demanding component. Problems in its development delayed the program. Only in 1972 did the first seekers suitable for installation appear, and their integration with the SUR-71 autopilot began. Due to the extreme secrecy that surrounded Soviet laser-guided munition development, typists who held the required clearance to print material on the matter were not permitted to write the word laser. Only the plant producing the seeker heads could do this, and so blank spaces were left so that individuals with higher clearance could write the word in by hand. Initially, to test the missile, Su-7B number 5130 was converted into the experimental Su-7KG, standing for Quantum Generator or Laser Designator, which would be used to guide the weapon during state trials. This was quickly abandoned after only 5 successful launches, as the Su-7KG did not possess the proper flight performance to guide the missile accurately. A year later, Su-17M No. 5101 was fitted with the Projector laser designator and renamed Su-17MGK to carry out these trials. In total, throughout the winter of 1973, 36 flights with 12 missile firings were carried out, including 1 salvo. Strangely, the primary issue experienced during these initial tests was not with the seeker, but instead the missile tumbling in the air, which was determined to be a result of a parasitic electrical charge caused by an uneven startup of the 2 27-volt DC power circuits. After this was resolved, the missile operated as expected, with the exception of it randomly veering off target moments before impact. The cause of this issue was determined by launching a salvo of 2 missiles. In this case, the missiles flew to opposite sides of the target, which allowed the team to determine that the culprit was the seeker and not the targeting system. Further analysis showed that when the missile came within 400 to 500 meters of the target, the reflected signal became so strong that the automatic gain control was overwhelmed, resulting in the seeker effectively blinding itself. To fix this, a new seeker with a greater gain control range was installed. The following year, state trials continued. 69 flights were conducted and 30 missiles were fired. This resulted in KH-25 beginning production in 1975. Shortly thereafter, it was refined to feature a lengthened tail section. MiG-23B No. 3224-3 and No. 3224-4 were also involved in these tests. The Ural Optical Mechanical Plant and the Sverdlovsk Production Association got to work developing a more advanced targeting system for use within Su-17 and MiG-27 immediately after KH-25 entered service. At the same time, Geophysica was instructed to begin work on Kyra. These systems would be designed in tandem, with Clen-P becoming a fallback option in case Kyra was impossible to actualize. Despite Kyra ultimately being successful, Clen-P was rather effective for its price and therefore saw wider application. I will not go into detail regarding the development of Clen-P, but it is important to note before I continue this section that in 1975, MiG-27 No. 323 was modified to operate the system, after which 5 KH-25s were launched. The same elements that made MiG-27K so good at delivering laser-guided bombs also allowed the aircraft to make excellent use of KH-25. It was possible to focus entirely on flying the aircraft, while the targeting system delivered the missile. The only input required on the pilot's behalf in this case was avoiding maneuvers exceeding 40 degrees per second. And yes, while I am aware that Ka-25 would technically be the correct pronunciation in English-speaking circles, KH-25 is more recognizable, and I don't want to create any confusion when talking about these missiles, and so I'll be using the technically somewhat incorrect designation because it's just easier to interpret for Western audiences. I hope that my Russian-speaking audience will not destroy me for this. Though it should be said that KH-25 was not without its issues. The missile could only be fired once the seeker had achieved a stable lock on the target. In unfavorable meteorological conditions, especially those which reduced atmospheric transparency, its acquisition range was significantly hampered. In certain cases, pilots could fall below the minimum engagement range because of this deficiency, which could have led to the aircraft damaging itself with the warhead. This issue would have been exacerbated in a conflict with the West, where obscurance would be abundant. It was for this reason that more advanced missiles were developed later down the line, which I will discuss shortly. Before I begin this section, I must note that I am omitting a relatively important development in this video, as it does not relate to MiG-27K. This is the KH-28, which was a missile commonly employed by Su-17 and Su-24 after the Yak-28P was given up in favor of these more modern airframes. I am making this known because it is seldom mentioned that the USSR conceptualized anti-radiation missiles alongside the United States in 1963. This missile was considered important as the USSR was beginning to realize that ground attack aviation was now more so than ever threatened by surface-to-air missiles. Looking at their own capabilities in this regard, the experience of the US in Vietnam in its pursuits to counter the S-75, alongside the inability for electronic warfare to inhibit the capabilities of a properly integrated air defense network, led to the independent development of modern SEAD and DEAD. It should also be noted that the Warsaw Pact defined electronic warfare as passive and active measures over the whole EM spectrum, including clutter. This is important as NATO defined this very differently, and you should know how I'm using this term moving forward. In 1972, due to general dissatisfaction with KH-28 and its capabilities, which I will describe later, Zvezda Design Bureau was instructed to begin designing a practical anti-radiation missile that was effective, reliable, and easily serviced. Though the most important and challenging requirement of this program would be creating a missile that could suppress SAM systems from outside their engagement envelope, permitting aircraft armed with KH-25s to destroy any remaining complexes while suffering minimal losses in return. It was decided to use the KH-25 as the foundation for this new missile, as it was already proven to be a functional design. Of course, significant changes to the system would be required, as alongside a new seeker, the team had to somehow extend the range of KH-25 by a significant margin. This was a tall order considering the distance in which Hawk could threaten Soviet aircraft. A new engine had to be developed, alongside a unique power supply and control system. But even with these integrations, it was impossible to attack systems such as Nike Hercules or Hawk without risking the aircraft, as it could only reach 25 kilometers. Because of this, a decision was made to narrow the target set for the new missile to more numerous low-altitude systems such as Kratal, which was an Army-level system, and Roland. This was reasonable considering MiG-27K was likely to strike targets that these systems were protecting. KH-58, which was not employed by MiG-27K, would handle the aforementioned longer-range complexes. It should be noted that the USSR had a very well-developed doctrine for SEAD and DEAD, and put a lot of stock into exceedingly long-range cruise missiles with anti-radiation capabilities. Another important distinction is that Hawk was one of the only medium-range anti-aircraft systems in service with NATO. The USSR and its allies had a much easier job designing all of their systems to counter this one threat, alongside Nike Hercules, of course. The PRGS-1VP Seeker, created by MPO Optimatica, is designed to engage continuous emitters in the A-band and features a capture cone of 60 to 100 degrees, enabling bearing tracking via both the main antenna lobe and its side lobes. It can detect and home on any one of 3 co-located radar stations that operate on different frequencies, transfer guidance in flight to an alternate station if the designated radar is switched off, and reacquire the target after signal loss or a carrier frequency change. The Seeker implements priority locking on illumination sources deemed most threatening and supports retargeting and launch against a different radar when required. The interchangeable PRGS-2VP Seeker is optimized for pulsed A-band emissions. It provides robust signal discrimination in contested electromagnetic environments and retains a short-term memory of the target's bearing when the emitter is briefly switched off, allowing continued monitoring of that sector. The PRD-276 is a 2-mode solid propellant booster with an 81 kg propellant load, a launch thrust of approximately 2,000 kgf, and a burn time of up to 11.5 seconds. An enlarged pneumatic accumulator powers the control actuators for approximately 90 seconds of guided flight, and the battery capacity was increased accordingly to support the extended electrical load. An element that had to be resolved on KH-27PS that diminished the capabilities of KH-28 was the missile trajectory. Early Soviet arms flew straight to the target, and therefore the angle of attack was determined by the altitude of the aircraft at the moment of launch. This was problematic as SEAD operations were ideally conducted at extremely low altitude to avoid being detected or engaged by the systems they were suppressing. If launched under the previously described conditions, KH-28 had a tendency to miss the target, which manifested as it often flying directly over the threat or landing behind it. This was especially concerning due to KH-28's tendency to blind itself when close to the target, leaving no room for correction. To solve this issue, KH-27 had to at some point climb to altitude before descending on the target from above. To facilitate this, the missile was fitted with a new autopilot, called SUR-273. This introduction allowed KH-27PS to continue flying towards a radar even after it had stopped emitting. The missile was finally officially granted the name KH-27PS, and underwent state trials in 1975 to 1976. After some modifications, it repassed tests in June of 1977 and was accepted into service in September of 1980. MiG-27K can carry 2 of these missiles, which receive their targeting information from an L-086 Vuga pod. Following the development of KH-27PS, it was desirable to unify missiles in service, as at this time there were 3 being employed simultaneously. Those being KH-23, KH-25, and KH-27PS. In 1978, the Minister of Aviation Industry approved the creation of a modular KH-25 family. OKB Zvezda minimized development costs by maximally reusing proven components. The PRD-276 engine, the SYP-273 autopilot, the F-27 warhead, power pack, and wings, and in the case of the KH-25MP arm, the passive radar seeker of KH-27PS. The laser-guided KH-25ML used the KH-25's 24N1 seeker, while the KH-25R employed a radio guidance suite based on the Delta PM-1 of the KH-23M. Throughout this family of missiles, the first compartment was often removable, as was the tail. The fifth compartment, in the KH-25MP and KH-25ML, did not contain any equipment, and in the KH-25MR, the sixth compartment housed the radio command guidance equipment. A distinctive feature of the KH-25MP is a slight indrawing of the body contours at the junction of the first and second compartments. The KH-25ML is equipped with a laser seeker incorporating a tracking coordinator with a 2-degree field of view and a target acquisition angle of up to 30 degrees. The missile measures 3.57 meters in length, has a launch weight of 295 kilograms, and carries an 86 kilogram warhead. It can be employed from altitudes between 50 and 5,000 meters at engagement ranges of 2.5 to 10 kilometers. The increase in maximum range from 7 to 10 kilometers compared with the baseline KH-25 was achieved through the use of a more powerful propulsion system and extended duration flight controls, though in practice this range is realized only under favorable weather conditions. The maximum velocity is 860 meters per second with a circular error probable of 4 to 5 meters. KH-25MR has a mass of 300 kilograms, including a 90.6 kilogram warhead, and can be used out to ranges of 10 kilometers. A high degree of commonality with previously developed designs accelerated the production and testing of the KH-25M. In 1981, 3 launches from MiG-27K number 1308 were carried out. That same aircraft would go on to launch 8 KH-25MRs alongside an additional 18 launches from MiG-27K number 14. Trials were completed in 1982, where MiG-27K number 1308 launched 1 more KH-25MP, 6 KH-25MR, and 5 KH-25ML. As the first phase of testing concluded, immediately a new variant was being workshopped, KH-25MT, which employed an electro-optical seeker. This gave way to KH-25MTP, which incorporated a thermal imaging seeker, enabling all-weather employment. Planned upgrades also included revisions to KH-25ML that promised a jammer-resistant upgrade of the 24N1 seeker, though this program was cancelled early in its development to focus on TV-guided weapons. Much of the KH-25M team would go on to create the KH-31P, which was employed by MiG-27Ks fitted with the Progress Pod in multiple instances throughout testing, and was planned to see introduction into the aircraft's arsenal, but the collapse of the USSR made this impossible. The only munition specifically designed for use with the MiG-27K would be the CAB 500L. Its development would coincide with the guided missile boom, meaning it could exploit the recent developments in seeker technology. Guided bombs had been proposed as early as the 1950s, but no system to deliver them existed, and the technology was lacking, which necessitated a long hiatus. The state scientific production enterprise Region, under the leadership of Privalov, was assigned to create this weapon. While the finer details of CAB 500L's development are largely unknown to me, multiple sources relating to MiG-27K describe its characteristics. The bomb had a mass of 534 kilograms, with a 360 kilogram warhead taken from Fab 500T. The system was made to use the Model 27N semi-active laser seeker. A sensor package mounted on the bomb's fins carried an optical tracker on a gimbaled boom, and a small computing device was built into the bomb's nose. After the bomb was released, the seeker's receiver turned on and locked on to laser light reflected from the target. The guidance computer and autopilot then adjusted the bomb's flight path to hit the object. Targets could be acquired between 3 to 6 kilometers depending on visibility. Ideally, the target would be identified at 10 kilometers. A circular error probable of 5 to 6 meters was achieved. Work that began in 1972 was successfully completed and the item was handed over to serial production within 3 years. In 1976, the CAB 500L began entering service. It was soon followed by the CAB 500LK, which carried cumulative submunitions intended to defeat armored targets. Later, the aircraft's arsenal was augmented with new bombs, the CAB 500KR and the CAB 500OD, equipped with television seekers and penetrating as well as thermobaric warheads. These later iterations were developed under the leadership of B.E. Mirtsalov. The TV gyro-stabilized seeker used a correlation-based target processor and comprised an electro-optical sensor mounted on a 3-axis gyro-stabilized platform, plus a single integrated electrical processing unit. The seeker permitted guidance from dusk to full daylight with a terrain feature contrast threshold of 0.2. Target acquisition range was around 5 to 9 kilometers. CAB 500KR munitions were intended for fixed targets and were released from level or dive profiles between 500 to 5,000 meters in altitude. Once the target was designated visually, the TV seeker was powered on and its video feed shown on the IT-23M display. When the electronic aiming reticle locked onto the target, the seeker stored the aim point by referencing at least 3 distinct landmarks and entered automatic tracking. After release, the bomb guided itself to the stored aim point with a circular error probable of about 4 to 5 meters. Employment of these weapons could be carried out in PKS or AKS modes. In the latter case, a higher probability of defeat was provided on the condition that the terrain was not monotonous and was sufficiently well illuminated. The electro-optical cabs, unlike Western systems that acquired targets by contrast using their light or dark edges, were guided by a reference image of the terrain and were capable of operating against low contrast and camouflaged objects, providing there were conspicuous landmarks around them. Night bombing could be assisted by flares from signal bombs. KH-25 was a capable system, but its warhead was lacking. All of its variants failed to exceed the destructive power of 100-kilogram bombs, which was problematic as attacking hardened targets was not an option with such an insignificant payload. The Molnia Design Bureau was contacted and informed of the need for a missile that could attack infrastructure, command installations, and fortified hangars. To meet these requirements, it became increasingly obvious that continuing the KH-25 lineage was not possible and that a radically new design was required, which interestingly took a lot of its aerodynamic principles from R-60. This new system was 1.5 times larger than KH-25. This size increase was required to facilitate the application of a significantly larger 317-kilogram warhead, 116 of which are made up of the explosive filler, an electro-optical seeker, and a new, more powerful engine. The new warhead was additionally fitted with a contact fuse, set to detonate the payload after penetrating the structure. The warhead was designed in such a way that ricocheting off the target is extremely unlikely, even at angles considered insufficient for earlier designs. The pilot launching the missile was able to set if the warhead's fuse was instant or delayed depending on the threat. The missile's airframe was made of 5 compartments: seeker, guidance control compartment, warhead, engine, and tail section, which can be stored separately and are assembled prior to its use using flanged joints. The missile's weight of around 680 kilograms and associated inertia required the adoption of a higher capacity onboard power supply. To increase the system's aerodynamic qualities, ahead of the control surfaces, fixed forward-mounted strakes referred to as load-bearing ridges were installed. Lateral stabilization is provided by conventional ailerons on the wing. Avionics and the seeker are powered by a thermal battery combined with an electromechanical AC converter, providing roughly 40 seconds of power. Two variants were devised. One was fitted with a conventional laser seeker, identical to 24N1 found on KH-25, which had a range of 8 kilometers. This model came to be known as KH-29L. KH-29L has two attack modes. One is a dive attack, in which the laser designator, the seeker, and the pilot's line of sight are aligned. Here the missile flies directly to the target. This mode is most commonly employed by aircraft operating CLEN. In the case of MiG-27K, Kyra can make use of the more advanced guidance mode. Here the missile is fired from low altitude, after which KH-29L then climbs to a height suitable for diving on the target from above. KH-29T, the more advanced missile of the two, employed an electro-optical guidance system, making it fully autonomous. The seeker comprises an electro-optical assembly with a target tracking coordinator, mounted on a gimbal and a processing unit that detects and registers high-contrast objects. Target acquisition can be performed either by the aircraft's onboard systems or visually by the pilot. Once the pilot has cued and picked the target with a laser rangefinder, the pilot assists the missile through the IT-23M to determine the object of the strike, through the missile seeker. To achieve more precise aiming, the pilot could switch the missile seeker from its wide search FOV to narrow FOV, yielding roughly 6-fold image magnification. By holding the reticle on the object, the pilot allows the seeker's contrast and spatial feature selection routines to isolate the target in the video feed. Once the target signature met the selection criteria, the seeker automatically transitioned to continuous tracking. After a final confirmation, KH-29T is released. Pilots were told colloquially that this missile is like a woman. It dislikes monotony and turns up its nose at any dust or smoke. If cloud cover was present, so that the seeker might lose the target by entering the clouds after separation from the launch aircraft, the pop-up Gorka mode was disabled and the missile began an immediate dive onto the target. The seeker is called Tubus 2, which is very funny, and in search mode offers a field of view of 12 degrees by 16 degrees. In automatic target track mode, the field of view narrows to 2.1 by 2.8 degrees. After 0.8 seconds after launch, the missile climbs to altitude and then dives to the target. While this figure depends on a multitude of factors, such as launch altitude, atmospheric conditions, target contrast, and target size, its maximum launch range is usually between 8 to 13 kilometers. The KH-29T sets itself apart from the KH-25 family not only via its payload and guidance mechanism, but its circular error probable, which was about 2.2 meters when launched from 4 to 5 kilometers. As a comparison, the laser-guided KH-29L typically exhibits 3.5 to 4 meters. While this is exceptionally impressive, it has its limitations. KH-29T cannot be used at night, or in especially bad weather, and most importantly, targets must be high-contrast objects. This family of missiles produces craters up to 12 to 15 meters in diameter and up to 6 meters deep. The heavy missiles required the use of the AKU-58-1 ejector rack, equipped with pneumatic pushers that displace the missile a safe distance from the aircraft after release, thereby preventing the engine from damaging the aircraft. Test pilot V.N. Kondurov described the KH-29 launch as tearing free from the aircraft with a visceral roar, so forceful that the little bomber would reflexively pitch its nose. Many interesting mishaps occurred when testing this advanced missile, which were of course related to the complexity of its design. The first of these anomalies occurred during a demonstration of the missile for Air Force Commander P.F. Kutakov in May of 1980. The test was designed to determine if KH-29 could pierce a fortified hangar. It was exceedingly difficult to detect the hangar against the spring foliage, and so by order of Deputy Commander Lieutenant General L. Supron, the shelter's doors were painted a bright color and a path of yellow sand was laid directly to the entrance. Finally, the missile acquired the target, but locked onto and struck the conspicuous sandy patch in front of the entrance, leaving the shelter intact. On another occasion at the Oktyabinsk range, V.E. Minitsky was scheduled to launch a KH-29 with a live warhead. This was rather important, as it was the first time MiG-27K had fired a KH-29 not armed with an inert warhead. Unfortunately, the system malfunctioned, and it took 6 passes to acquire the target. Further issues arose when attempting to fire the missile, as the MiG-27K would not release the weapon. This was extremely concerning, as despite the engine failing to start, the tracer meant to assist the pilot in picking out the missile as it flew to the target was burning like normal. This understandably terrified Nevsky, as he believed it could somehow ignite the warhead. He said the following upon landing safely: "I suddenly felt with my whole skin that beneath me was a powerful missile, capable of completely destroying an entire city block, and even a single fragment would have been enough to destroy my aircraft." To many it appeared these trials were cursed, as sometime after the incident involving Nevsky, a guidance malfunction caused a KH-29L to fly a significant distance from the target and crash near an airfield where an expensive and exceedingly sensitive Mikoyan prototype was being prepared for flight. Had the missile struck within 100 meters of the aircraft, that day could have been a tragedy, but luckily this missile carried an inert warhead. What was especially surprising about this event was that the KH-29 flew further than what was theoretically possible, leading aerodynamicists present during that incident to state that it was likely controlled by a demonic force. Of course, these problems were resolved and the missile entered service later that year. KH-29L was used extensively during the Soviet-Afghan War to strike hardened targets such as caves and bunkers. There is a very common misconception that surrounds strike aviation throughout the Cold War. In a scenario where the Cold War goes hot, fixed-wing aircraft are not going to be attacking tanks, they're not going to be attacking APCs, they're not going to be hitting infantry in range of artillery. This just isn't going to be happening at scale. There is no reason to waste airframes doing this. In a conventional conflict, it is not only exceedingly dangerous to do this, but wasting aircraft that could be doing much more important things tens of hundreds of kilometers behind enemy lines doesn't make sense. The obsession with CAS seems to come from recent conflicts, which are less conventional in nature, where a lot of the descriptions of air power are coming from the infantry's perspective, usually surrounding aircraft like A-10 and so on. F-111s would not be blowing up individual tanks, and MiG-27 wouldn't be doing that either. The same applies to Su-24 and all of these more capable strike aircraft. Of course, subsonic strike aircraft like Su-25 and A-10 and all of these planes may be doing these tasks, but even in these cases, it's exceedingly dangerous for very little gain. Strike aircraft would overwhelmingly be doing things like hitting rail junctions, bridges, storage facilities, industrial assets, radars and air defense sites, command sites, vehicle parks, repair plants and other logistical hubs, harbors, hardened aircraft shelters, air bases. These are all places where precision-guided weapons are incredibly important, especially at range, and neither side seriously planned to waste them on individual armored vehicles. That's absurd. The reason that PGMs are important is because these high-value fixed targets are simply too hardened to be destroyed by a near-miss with a conventional bomb. It's just not possible. KH-25 and KH-29 were designed to hit bridges and trains and buildings. They weren't designed to hit singular tanks. This is a very strong misconception that surrounds almost every PGM. When you look at aircraft like Tornado, F-111, and Su-24 especially, they were designed to hit important targets behind the front. That's why they had to fly low and fast, because they had to get behind air defense. Before attacking a target, the pilot presses the button "Permission to fire." After the fire command is given, the battery and the gas supply block are started in the following sequence. In the control system, a DC voltage of 36 volts with a 1000 Hz excitation is applied to energize the pyrotechnic supply. As pressure rises and pneumatic lines reach the required level, the pneumatic interlocks on the pyrotechnic devices are released. After the required pressure is achieved, the battery supplies the pilot's pyrotechnic firing circuit with a positive 27-volt bus voltage to arm or unblock the missile squibs, and pyrotechnic elements to enable release of the mechanical locking devices. The current then flows to the electrical circuits in the missile, and the battery bus at approximately 27 volts. When the current consumers in the actuator drives are switched on, for example after the allow actuator movement signal, the positive 27 volts is also applied to the control circuit through a time delay relay. After that time delay relay, the transmitter's time delay relay provides a positive 27 volt pulse at its output through the time delay chain to initiate further stages of the firing sequence. On disconnection, the signal returns to the aircraft receiver as ready. After that return, the mechanical block of the AEU control device is released. The mechanical stops that previously prevented movement of the servo mechanism are disengaged. The switch then disconnects power to the pyrotechnic unit and is set to armed, which establishes the ready state. The timer signal in the firing circuit issues the separation command. After complete mechanical separation of the missile from the aircraft, the pyrotechnic separation charges are fired. In practice, this ignites the rocket motor initiator, and the pilot sees the separation indicator on his panel. After separation, the missile control unit generates the engine start signal, directing the control channel to the appropriate relays. This causes firing of the pyrotechnic elements that start the rocket motor. In case of failure in the missile firing sequence, the aircraft places the missile in the safe condition. After approximately 2.4 to 0.7 seconds, the missile is made safe. Any initiated elements are inhibited from firing the missile, and it is secured for transport. In this diagram of the pyrotechnic block, we can see the following elements. The pyrotechnic block consists of a casing containing the pyrotechnic charge and the ignition device. Upon applying an electrical impulse to the pyrotechnic block, the igniter fires the charge. The gas produced flows through the openings in the filter and the T-fitting to the actuator, and to the battery. Rigid tubing is present, intended for connecting the pyrotechnic block to the actuator gas system. They are connected by clamps, screws, and gas-tight joints. The T-fitting is used to connect the rigid tubing of the gas system with the battery. For connecting the battery to the T-fitting, a short section of flexible tubing is used, permitting a degree of movement. The solid propellant rocket engine, PRD-280, is located inside the rear body compartment and secured to the frame. It is protected by a heat-insulating casing. The engine housing is attached to the missile body by 4 support brackets and a clamp. On the rear face of the solid propellant rocket engine housing, to which the missile's tail section is attached, are mounting connectors and elements for the igniter system. PRD-280 consists of the casing, the ignition unit, and the nozzle. The nozzle is a conical element equipped with a thermal insulation liner and a throat insert. At the front of the casing, a threaded igniter chamber is attached and reinforced with a retaining collar that holds the igniter charge. Only the nozzle assembly is attached to the airframe by means of clamps, while the casing cover with the igniter is screwed in together with a retaining collar. Inside the igniter chamber is the igniter charge, enclosed in a pressed casing equipped with 2 electrical initiators. The igniter charge serves to ignite the main propellant charge of the rocket motor. The firing of the PRD-280 rocket engine occurs after a voltage of 27 volts is applied to the igniter terminals. The resulting electrical impulse ignites the igniter charge. The generated flame front passes through the igniter nozzle and ignites the propellant charge. Combustion of the propellant charge takes place inside the combustion chamber and nozzle. The produced gases expand through the nozzle throat, generating thrust. The engine has a mass of 110 kilograms, and a propellant mass of approximately 192. The power supply system is designed to maintain power to the missile's electrical circuits, actuators, and onboard systems. The basic component of the power supply system is the battery block, which, together with the intensive heating block, forms a single unit. The battery is a source of direct current, providing electrical power to the missile. The electrolyte of the battery is solidified, so prior to flight it must be heated to restore conductivity. For this reason, an intensive heating block is installed, enabling rapid melting of the electrolyte and bringing the battery to operating condition. Upon receiving the heating signal, a current of 27 volts is applied to the heating element. The heating element causes temperature of the electrolyte to rise. Once the specified value is reached, the battery automatically begins to operate. The battery is designed to operate for at least 60 seconds after activation. The battery temperature is regulated by a sensor, which is a bimetal thermostat. After reaching the preset temperature, the thermostat switches off the heating circuit. When the temperature drops below 70 degrees Celsius, the thermostat again switches on the heating. The heating system keeps the internal battery between 70 to 75 degrees Celsius. The battery is charged at the factory. Distribution Box 9-70 is the electrical distribution and power supply junction for the explosive and pyrotechnic initiators located in the warhead section. All electrical components are installed inside the box enclosure. Wiring harnesses run from the distribution box to the respective sections, and each harness connector is fitted with a rubber seal to provide environmental protection. 5 wiring harnesses enter the warhead unit. The KMU-63 igniter assembly consists of the electrical igniter and the electric safety device, which prevents the transfer of the firing impulse to the igniter until the proper sequence is completed. The KMU-63 set includes electrical cables and connectors for connection to the aircraft's firing circuits and to the rocket engine igniter. KMU-63 contains 2 contact sensors. Contact sensor B-168 is installed in the compartment number 2 of the missile. Contact sensor B-168 is a very standard crush sensor. The main components are 2 reactive contacts, each consisting of an inner and outer electrode. When the missile meets the target, the missile's nose section collapses and closes the sensor contacts. A signal is issued to trigger the KVU, which detonates the warhead. The more interesting B-169 reactive contact cable sensor is installed on the leading edge of each wing and are fastened with clamps. The main element of the reactive contact cable sensor is a heat-resistant dual coaxial cable. The central conductor serves as the inner contact of the sensor, and the inner braid serves as the outer contact. When the missile meets the target with its wing, the wing deforms and compresses the cable, which causes the central conductor to short to the inner braid and accordingly trigger the warhead. The B-169 explosive ignition cartridge is installed within the igniter housing and is initiated by electrical impulse applied to the igniter leads. The cartridge produces a strong flame jet which penetrates the igniter nozzle and ignites the main propellant. The igniter is actuated by 27 volts being applied to the igniter terminals. A protective safety relay prevents actuation of the igniter until the firing command has been issued, and the pyrotechnic safety is unlocked. The igniter action time is about 1.6 to 2.5 seconds, depending on temperature. The steering drive unit receives 3 drive outputs from servo drive PS-12. These drive lines connect to control rods inside the warhead and actuator compartments. The drive motor is mounted to the missile frame and linked to the control shaft. The 1 and 2 channel transmitter blocks consist of the following elements: Channel 1-2 transmitter block, automatic block, stabilization block, power supply block, electrical system, and associated cables and connectors. The transmitter block 1 is the main steering element. The transmitter block 2 ensures stabilization of the projectile in flight and compensates for disturbances. Transmitter block 3 stabilizes the seeker. To ensure aircraft safety at the moment of launch, the control system is turned on automatically after a short delay of 0.8 seconds. During this time, the projectile is stabilized on the flight path and moves away from the aircraft to a safe distance. The projectile's steering and stabilization occurs in 3 non-interacting channels: 1, 2, and 3, which I described earlier. Channel 3 is also responsible for automatic height correction and control of the projectile on the target. The circuits for all these channels are identical. Tubus 2, or TVGS2, is designed to guide the projectile to the target. The television camera is responsible for converting the target image into an electrical signal which is transmitted via the electronic system to the steering unit. The target image is projected through an optical system onto a photodetector. The voltage generated by the photodetector creates a control signal for the steering system. The resulting electrical signal is processed through the television camera and the gyroscope stabilization unit. Signals are generated as needed and fed to the control circuits. The TVGS uses a line scanning method from top to bottom and left to right. The number of lines is 625, with a field frequency of 25 Hz. TVGS operates in such a way that even with changing external lighting conditions, the signal at the detector remains constant due to automatic gain control, and the target is reliably tracked across a wide range of illumination conditions. Now, if you ever wake up as a KH-29T, you will be able to get out of bed and go through your morning. I hope this was helpful to the 5 people that wanted to know everything there is to know about KH-29T. I find it interesting, so hopefully one of you do as well.
The aircraft could now perform with high precision in any weather, day and night. Besides, this gave not only a passive chance to escape means of air defense, but actively attack them.
One MiG-27 pilot says the digital weapon system is so smart that if you placed an officer's hat on the ground, he could hit it from many kilometers away.